here is probability density functions. Okay, and these are for continuous variables. Okay. And in this case, now, and we call these PDFs with lowercase PDF, so that's lowercase. And so that's why I like CDF and not uppercase PDF for the cumulative. But here, this is nice. For the continuous case, we can just define f of x to be the derivative of big F of x, the CDF, with respect to x. And it's that simple. Now, what we know is that f of x will have to be greater than or equal to 0 since f of x is increasing, or at least non-decreasing. And then our relationship, similar to our summations for discrete, an integral is really just a sum of things. F of x is the integral from minus infinity to x of little f of s ds. Now I've switched variables because we've got an x up there. And so what that also means is that the integral from minus infinity to infinity of f of x dx has to be 1. And so then from that, if similar to before, if we say, okay, I want the probability A is less than X is less than or equal to B. Well, now we'll see, because of the way we're defining this, that, well, I could have made that A less than X is less than B. I could have made it A less than or equal to X is less than B, or I could have made it the probability that A is less than or equal to X is less than or equal to B. They're all the same in the continuous case. And that we get from f of b minus f at a, but fundamental theorem of calculus says, oh, that's just the integral from a to b of our little f of x dx. And so continuous is really pretty simple as long as I can do the antiderivatives. An example of this is the exponential distribution. And actually, this is a whole family of distributions, the way this is being written. Exponential distribution. Here we define f of x to be ae to the minus ax for x greater than or equal to 0 and a greater than 0. So this parameter a needs to be greater than 0, and then 0 otherwise or everywhere else. Okay, so that is the exponential distribution. And so, if I wanted the probability that, say, 1 is less than x is less than 3, or even less than or equal to, as we did, well, we would want f of 3 minus f of 1. But again, fundamental theorem of calculus, that's just the integral from 1 to 3 of a e to the minus ax, because that's little f of x dx. And I would get that. Now, actually, I know the antiderivative of this. This is just e to the minus ax. So we haven't given a particular value of a, but it's just e to the minus, minus e to the minus ax. And so then this is, I put in them 3, so minus e to the minus 3, 3a, right, that way. And then minus a minus e to the minus 1a. So if I know a, then I could figure that out. And so that's an example of that. Now if we go here, so here I've picked different values of a, and I can change those. So they're, I had it on 0.75, 0.66. And I define f of x to be a e to the negative ax for x greater than or equal to 0. And so there's the plot. It's just that tail of an exponential function. But then I can define big F of x as this interval or integral, and there it is. And notice, it is increasing, and it is heading, there's 1 up there, and the green line is heading toward 1 as we head out to infinity. Okay, so it looks like it's doing what it's supposed to be doing. And I did f of 2 and got 0.73. Now that, of course, will change with a. If I make that up to 1.2, it's 0.9. And f at infinity is 1. Now I did find that as I changed a, you got round off error at times, and that 1 changed to 0.99 something. And so if I just kind of move this around, you'll see it jump in there at times to something not 1, but almost 1. But that's just round off error in the code. So that is the idea of a probability density function and its relation to its cumulative distribution function. And so I think that finishes out 3.2. Oh, no, it doesn't quite. They're still mixed, but we'll stop here.